We're looking at 3.7 optimization problems. Now, this is probably one of the most common applications of calculus, honestly. So this is, kind of an important lesson. So one of the most common applications of calculus involves the determination of minimum and maximum values. So here's what you want to do. Here's your guidelines for minimum and maximum problems. Now, don't freak out. This is going to sound a little bit like related rates. Remember, related rates are pretty tough, right? But at the end of the day, I'm going to say it's closer to elimination and doing like elimination substitution, more so substitution. You do like partial substitution, then differentiate. That's kind of what it comes out to be. Okay. All right. So guidelines for solving applied minimum and maximum problems. First off, you want to identify all given quantities and all quantities to be determined. If possible, make a sketch. Write a primary equation for the quantity that is maximized or minimized. Reduce the primary equation to having a single independent variable. This is the important part. This is where this changes from related rates. Related rates, we could have multiple variables, right? This one here, we only have one. Good? Hmm? All right. So we want to get down to one single independent variable, and we might have to use a secondary equation for this one. Determine the feasible domain of the primary equation. That is, determine the values for which the stated problem makes sense, and then determine the desired maximum and minimum value by the calculus techniques in 3.1 to 3.4. All right. So here we go. We got manufacturing. Wants to design an open box having a square base and a surface area of 108 inches, and he wants to figure out how to get the max volume out of this thing. Okay? So, let's draw a picture. Here's a box. Oh, it was good in the last line. Good enough. How about that? Gosh. All right, there we go. And the top is open. All right, so we want to do this guy. We want to have a square base, and the square base and a surface area of 108. All right, so let's just write that there. We want a surface area of 108, and we want a square base. So we're going to need two things, really. We're going to need the volume, and we're also going to need surface area eventually, right? All right, so first off, volume formula, I'll just recap back. Volume formula is big B times H, the area of the base times H. And surface area is area base plus area of the sides. Typically, it's 2 times the area of the base because that's if you get the top and bottom. I left off the 2 because we only need the bottom. We don't need the top. All right, so let's figure this thing out. We want this box to be a square base, so let's just call both sides x. That base is the bottom is going to be a square, so they'd both be the same, right? And we'll just call this the height. So in our case here, then, our volume formula is going to be x squared h. Agreed? X times x would be the area of the base times the height. So we have x squared h. And then at the same time, the area of our surface area. So our surface area would be area of the base, which would be x squared, plus the area of the sides. So we're going to have 4 sides, right? And they would be x times h, wouldn't they? Like the area of this end here. All right, the area of this guy would be x times h, right? In fact, it's a square, that all have to be the same. So we'd have 4 times xh. Now we also know that that's equal to 108, don't we? So 108 equals x squared plus 4xh. Now, if we look at this guy, we're worried about volume, correct? big thing we want max volume. Now, if we want to be max volume, we want to be able to get this now in one variable. So I'm looking at this. I have an x and an h. This one, x, h, right? And we're worried about x. So can we solve this guy for h and then plug it in over here? Yeah. So let's solve this guy for h. So I'd have to subtract over x squared. 108 minus x squared is 4xh. And divide both sides by 4x. All right, so then h is equal to 108 minus x squared over 4x. With me so far? Yeah? Bella, you good? All right, so let's plug it in for h. So volume is equal to x squared times 108 minus x squared over 4x. All right, so then if I go ahead, I'm going to end up with 108 x squared over 4x minus x to the fourth over 4x, right? What's that? I split it up, yeah. So that's going to be 27x minus x to the third over 4. Go with that? All right, so there is a formula that relates our x to each other and also relates surface area and volume into one formula. Okay, so we just kind of did some substitution. Now, let's find, this is still volume, let's find dv dx. The dx would be the derivative of the volume with respect to x. So what's the derivative of 27x? 27 minus, and then we'd have to, could essentially split that into 1/4 x to the third, right? You do that constant multiple rule. Then you get 3x squared, bring it back together. So you get 3x squared over 4. All right with that? Okay? So that is the derivative of this. All right? Now, derivatives, to find critical values, we set this, our derivative equal to 0, correct? We did that like in 3.1, 3.2. So let's do that again. 0. Take the 27 over, and then I'm going to multiply by 4, negative 4. So I have negative 27 times negative 4, 3x squared equals 108. Divide by 3, x squared is equal to 36. Square root of both sides. What's x equal to? Plus or minus 6, right? With me? Now, those are my two critical values, essentially. Now, looking at this, that's my side length for x. Is there any way I can have a side length of negative 6? No. So the negative doesn't work. Therefore, I have a max value when x equals 6. Okay. Now, plug that back in. H equals 108 minus 6 squared over 4 times 6. 108 minus 36 over 24. It's going to end up with 3. Okay. So I have a max volume when x is 6, when h is 3, and the dimensions would be 6 by 6 by 3. That gets my max volume based on the parameters given and having 108 inches of surface area.
What's H equal? 3.
3. The bottom, this would be the bottom, this would be the base of it, and this is the height. All right? It's kind of cool, isn't it?
Forever.
I think it's kind of cool. Took forever. Questions?
I think this is definitely an example one.
All right, let's look at one more. We'll call it a day. So, when we're going to find minimum area. So we have a rectangular page contains 24 square inches of print. The margins at the top and bottom of the page are 1.5 inches, and the margin on the left and right are to be 1 inch. What should the dimensions be to minimize the amount of paper used? Okay, let's draw a picture. There's our piece of paper. Okay, now we have 1 inch margins and a 1 inch margin. And then we don't know this distance here, do we? Let's call that one y. We'll call the other one x. Okay, so there's that one. Over here, I have 1.5 inch margin, 1.5 inch margin. In between, we'll call that guy x. All right. Now, obviously, it says rectangular pages contain 24 square inches of print. All right, that's just the print. That's not the size of the paper. That's just the print area. Now, obviously, area formula is just length times width. Agreed? All right, and then we also know that just the print area would be our x and y places, and that's 24. Okay? This is just the print area. The one on the left is going to be our area of the entire thing. All right? So this entire thing, my length would be x plus 3. Okay? The x value on the side plus 1.5 on top, 1.5 on the bottom is 3. All right? What would my width be? Y plus what? 2. Y plus 2. All right, now I got two things going on here. This is my primary equation here. This is my secondary. I got x's and y's in this first one. Second one, I have x's and y's. Let's get rid of the y. That work? So let's just solve this secondary one for y. So y is 24 over x. Now I'm going to plug this in over here. Area is equal to x plus 3 and then 24 over x plus 2. Good with what I did there? All right, then we FOIL. We FOIL and combine like terms. We're going to end up with 30 plus 2x plus 72 over x. I just saved you a simplifying step in there. So that now is our area formula relating those two things. All right? Now, from there, let's find our derivative. dA dx. It's the derivative of a with respect to x. So 30's gone. I get a 2. And then I'm going to have minus 72 over x squared. If I would factor that guy, or find the derivative of that guy. All right. So there's my derivative. Set it equal to what now? 0. Okay. If I could take the 2 over, so I have negative 72 over x squared, negative 2. Multiply both sides by x squared and have negative 2x squared negative 2x squared equals negative 72. Divide both sides by negative 2, so x squared is going to be 36. Over both sides, x is going to be plus or minus 6. And no, not every answer is going to be 6 for x. Now, is negative 6 a valid answer here again? No. All right, so x is going to have to be 6. If x is 6, then y is going to be 24 divided by 6, which is 4. All right, so the printed area should be 6 by 4. And then the dimensions of the entire paper are x would be 6 plus 3, which is 9. Our y would be 4 plus 2, which is 6. This would be our dimensions. If we're going to have 24 square inches of print on a piece of paper with those margins, our prime example would be making the print area 6 by 4 and the entire paper 9 by 6. Questions? Anybody?